Okay, let's do one more Aspen tutorial, just playing around with these distillation columns. Hopefully I'm sharing my Aspen screen here. Good, let's start a new one. Okay. And we're gonna look at a case study for distillation. However, this time we're dealing with three components, right? Let's start out the classical three-component mixture where we have benzene, toluene, and cumene, okay? And what we're going to do is we're going to run the DISTWU model first to get basic estimates, and then we're going to put this into the Radfrac model and run it, and also have a look at the different different details of the column. Maybe try to have a look at on putting in some internals and then seeing how this is going to work out. So again, we said we have three components. Toluene showed up here. Just make sure these two guys show up. Toluene. We said benzene. Okay, and then the third one, cumene. Isopropyl benzene. Just make sure that it shows up in these two. And for the equation of state, let's pick SRK. You can pick any equation of state you want. I like SRK. It works reasonably well for a lot of things. Okay, so SRK here, and then you see my parameters is red. So I'm gonna expand this tree. I'm gonna expand binary interaction. I'm gonna click on it right here to clear so that it retrieves this information. Okay, and then this red circle should disappear. Okay, good. Now let's go to the simulation. And I'm gonna do two things. First of all, I'm gonna run the shortcut method to get some initial details, and then I'm gonna use the Radfrac method to try and get more design information. And again, your shortcut methods in Aspen are very similar to McCabe-Thiele. They are used for initial estimates, right? They won't give you the best answer. They won't give you the final answer. However, as a good initial estimate, they are a useful tool for that purpose. Now, then you can use the Radfrac model, which we're going to do in a bit, to try and really look at the internals, the type of tray you want to use, number of stages, detailed profiles. This is what the Radfrac model is for. But this has the same utility as McCabe-Thiele, right? Just to give you initial estimates of the number of stages, etc. So I'm going to have a feed, I'm going to have a distillate, and I'm going to have a bottom. So let's call this feed. Let's call this guy here top. Yeah, remember, it doesn't like top. Let's call it distillate. Let's call this. Okay, so let's call this DSTWU try or DSW 1. Okay, so I'm just trying this shortcut method. Actually, let's call it shortcut. There we go, shortcut. Good, so this is a shortcut distillation column. I'm gonna specify my feed. I'm gonna specify these two guys. So let's have a look at the feed. And you can feel free to specify whatever you want. Feel free to play around with this. So just try to get an understanding. And I'm gonna specify a saturated fluid, saturated gas, right? So vapor fraction is 1, and the pressure is, say, 1 atmosphere, okay? So it's a saturated vapor at 1 atmosphere. Total flow rate is 1,000 kilomoles per hour. And I have a mass fraction here. Specify actually mole fractions. Let's say it's 30% toluene, 40% benzene, 30% cumene. Okay, so I just specified the basics of the stream entering this column, and then I'm going to go back to my main flow sheet, and I'm going to click on the shortcut column here to specify some parameters. And as we said, can specify either the number of stages or the reflux ratio. I'm going to look at the reflux ratio. And when specifying the reflux ratio, if you have a number in mind, you can always put it. if you don't have a number in mind and you want to operate as a factor of your minimum reflux ratio, then it will be, so you need to put a minus. So if I want to operate at reflux ratio, which is 1.25, the minimum reflux ratio, I'm going to put minus 1.25. I want to operate at 1.5, the minimum reflux ratio, minus 1.5, etc. So you add this minus when it's a factor of your minimum reflux ratio. And then we'll just operate it at atmospheric conditions. So let's call it 1 and 1. Just thank you. Maybe specify them in the right order, reboiler first and then condenser. I'm going to use a total condenser, and here we need to specify our recoveries. So for my light key, so in this case, my light key will be toluene, and I want a recovery of 0.95, and this is the heavy key. And one thing we did, I think we did an error last time actually, where we didn't correctly define this, because I think last time I defined this as the recovery of the heavy key in the bottoms. Okay, however, this is actually the recovery of the heavy key in the distillate. So just go back to the previous tutorial, and if you submitted it, that's fine. If you didn't submit it yet, or you're still working on it, just maybe do the math, or calculate the recovery of the heavy key in the distillate, which is the top stream, and enter the number and see what you're gonna get. So in the distillate, I should not have a lot of cumene, so that's only 5% recovery from the top, and this should define my column. Okay, and again, just a comment here that this is actually the recovery of the heavy key in the distillate, which is the top stream. Okay, it's not the recovery of the heavy key in the bottoms, as I mistakenly said last time. So just be careful of this issue, and maybe if you go back and you do it, you're gonna get similar numbers to the Cape Feely actually, or closer numbers than the Cape Feely. Okay, now we have everything. Let's run this simulation, and we should be able to see some numbers. It's gonna take some time. Give it the time. Okay, so now it's completed. So now let's go to the results and have a look at these results we get from this shortcut method. And as you can see, this time it worked fine. Sometimes it will not work fine for you. If it doesn't work fine, you can still use the numbers you get from the results as useful input for the Radfrac. And I think the issue last time is that I confused the recovery of the heavy key here in the distillate with the recovery of the heavy key in the bottom. So yeah, because when I ran it before, it worked fine and then it stopped working. So I just fixed that number in the previous tutorial and it should be fine. Anyways, let's have a look at the results in our case here and come to office hours if it doesn't make sense. But anyways, let's have a look at the numbers we have. So our minimum reflux ratio is 0.76. Our actual reflux ratio is 0.96. Minimum number of stages, 5. Actual number of stages, 11. Number of stages above the feed is 5.2. You have your reboiler heating, you have distillate to feed fraction. So we have a lot of information. So let's take note of this. Let's go back to our main flow sheet and let's drop our Radfrac column here. So I'm gonna put our Radfrac. I'm gonna call this detailed, okay? And I'm gonna replicate the same thing. So I have here this feed. I have a vapor distillate and I have a bottoms here. And let's call this RF top. Let's call this RF bottom. Let's call this feed 1. I'm gonna just replicate the exact same thing we did here. So let's open the feed 1 first of all. And we said we specified the vapor fraction. We said saturated vapor, so 1 at a pressure of 1 atmosphere. All right, 1 atmosphere. We said the flow basis, so it's 1,000 kilomoles per hour. Right. And we have our fractions to be 0.3, 0.4, and 0.3. Okay, so now let's have a look at the detailed, or this is the Radfrac model here. This is my Radfrac model, and this is the shortcut or the DSTWU model. So open the Radfrac. Let's have a look. What do we need to specify? So we need to specify our number of stages, okay? And we're running at equilibrium, so I want to specify my equilibrium number of stages. So we already have an initial estimate from the shortcut method, and this is the number I'm going to use. So my actual number of stages is 11.19, so I'm going to use 12. And we're going to use a total condenser. Actually, not the total condenser, let's use a partial condenser, right? What did we specify in our shortcut method? Let's have a look here. What did you specify a total condenser? You specified a total condenser. That's fine. I mean, you usually specify total condenser to get your minimum number of stages at total reflux. However, when you're actually operating, you don't run it. You don't run a total condenser, right? You need to run a partial condenser with a reflux ratio. Total condenser means total reflux, right? Doesn't make sense. Or, you know, it has its own purpose, certain configurations, which is not what we want to do. Okay, kettle, valid phases, vapor liquid, standard, and I need to specify 2 things here. Let's see what we have from our shortcut product results, which we can use in this case. So I'm going to use the actual reflux ratio, 0.9619, and I'm also going to use the distillate to feed fraction, 0.699. So I'm going to use these 2 numbers in my Radfrac. So we said the first one was, what was it? It was the actual reflux ratio. So reflux ratio here. And let's see, actual reflux ratio. It is 0.96. Let's just keep the 0.96, that's fine. 0.96. And then the second metric I'm going to use will be the distillate to feed ratio, which is 0.699. Let's use 0.7. So distillate to feed, let's just find it from the list. And I'm going to put 0.7. Good. So now I have all this information. Configuration which we took, number of streams here. I need to specify the feed stream, right? And the shortcut results give me some information about location of the feed. Feed stage should be at 6.25. Okay, so I'm gonna put my feed stage to be, let's call stage 6, right? And above stage or add stage should be fine. However, it was 11 and we made it 12, so let's keep the 6 and above stage. And pressure, I'm gonna operate this at 1 atmosphere. And that should be enough for the Radfrac model. Okay, so now I put in all my details here. And if you run this, you're gonna get some results from Radfrac, and the results still give you a problem. They'll give you recoveries very similar to what you specified in your shortcut method, right? However, this is not the utility of this Radfrac. Utility comes here where I click on design and specify column internals. And here you can really add some more details. And you know, once I click it, tells you simulation is missing hydraulic data. Let's generate this hydraulic data and let's start having a look on how we can really deal with this. Okay, so you now see the column, and let's do something. Let's divide this column into 2 stages. Let's divide the first one at above the feed stage, right? Let's go from 2 to 6. 2 to 6 is I'm gonna have this sift with sift trays, and let's specify it from 7 to 11, and let's have this to be bubble cap. Okay, so now I specified my column with two types of packing. The first one is the sift trays above the feed, and then I have bubble cap below the feed. One thing you need to be aware of is where your stages start and where they end. So maybe I want this to make this 2 to 5, and then make this, 6 to 11. You can always do that. Maybe 6 to 10. You can always control where your stages start and end. But I'm gonna keep it conventionally. I have 2 to 6 for my feed, and then 7 to 11 for my for below the feed. And you can see you have other parameters. You have number of passes, you have your tray packing, you have all of this stuff, which you can specify if you want it. Okay, so the important part here comes when I click on View Hydraulic Plots. So if I click on View Hydraulic Plots, this will really give you information about the flooding. I'm not sure if you've taken flooding in mass transfer, but I think we covered it briefly in design. But flooding, it will generate basically a plot at every stage. And some of these plots have excess, means, we're operating outside the normal hydraulic conditions. So hydraulically, it's not going to work out. You're going to have flooding, you're going to have weeping, you're going to have dumping, all of these different things. Let's have a look at the stage that works. So stage 6, everything looks fine here. Seems that it's working fine. So stage 6, so let's have a look, sorry, at stage 6 here. This is my operating point. This is where actually my column exists. And this is the hydraulic charts where, this is the maximum entrainment. Here I have some weeping at this point. Here I have dumping. So weeping is when, you have some liquid drops falling down from the tray and falling to the tray below. Dumping, where the liquid is just being dumped on the tray below. There's not enough vapor pushing this liquid above. Flooding is when the liquid is not flowing downwards, right? It's just, you have a reflux and you're sending the reflux down, but the liquid is not actually flowing downwards. It's being held up by the gas. And ideally, you don't want to have weeping and you don't want to have flooding. So if you open your hydraulic plots and you find that some stages have flooding here, you want to change your conditions to solve this. So if I look at stages, so all of the stages above the feed, they all have flooding, right? It's not going to work out. So this is my operating point, and this is where I want to typically operate. I want to operate within this envelope where I'm operating at a very high vapor flow rate versus liquid flow rate. My vapor flow rate is so high compared to what is acceptable in this column. So my vapor flow rate is so high, it's going to keep on pushing the liquid up. It's going to prevent this liquid from the reflux to flow down the column, and you're going to have flooding, right? You're going to have flooding, your column is not operating properly, it's not going to work out. So you need to find ways to solve this issue right here. Okay, so how do I fix this this issue? You can try to decrease the reflux ratio. So I can go to my Radfrac column, and here comes really the utility of the Radfrac column, because even though the shortcut method or maybe McCabe-Thiele will give you some numbers, when it comes to the actual hydraulics, once you specify type of packing you want to use, you can really now zone in on the best operating conditions for the equipment you want. So I have flooding on all the stages above the feed. So let's see if I decrease the reflux ratio, if it's going to have any effect. Let's make this 0.85 and see if this will affect my hydraulic plots. So I change it to 0.85. I'm going to run my simulation and see if I see any changes. Give it some time, it will take time to run all of these simulations. And now results are available. Okay, let's have a look at the hydraulic plots. You can always click on them from here, or yeah, let's click on them from here. That's fine. And what's this column, hydraulics? Let's see what this shows us. Yeah, this just gives you a summary. You know, total height, you know, it gives you a lot of details about the different things. So let's have a look at the hydraulic plots and see if we're able to solve this flooding issue. As I can see here, I still have a problem here, you know, it's not working out, it's still flooding. Okay, and all the stages below the feed, it's fine. However, let's have a look at stages with warning, stage 7, stage 8. It's fine, but I'm really pushing it, right? You know, I'm just operating on this line. I'm very close to starting to have weeping, and this is because of flooding. Right? If you solve this problem, this will get resolved. Okay, so reducing the reflux ratio did not solve it. So we forgot to do something. Logically, if you reduce your reflux ratio, you want to increase your number of stages. Okay, let's increase the number of stages to, let's say 16. It's fine, let's increase it to 16. And let's go to our column. Or let's look at our column, and now let's increase the packed section above the feed. Maybe if I increase my packed section above the feed, this will avoid this issue. Okay. Let's go to Radfrac. Let's go to specification. Sorry. And let's look at design and specify internals. And to basically want to make this from 7 to 15, right? Okay, one thing which you could also do, if I click on view internal summary, maybe not view internal summary, if I look at, no, I go back to my column internals, maybe not this, not what I'm looking for. I want to close out of this. I go to my Radfrac specifications, click on design column internals. If I look at view, so here in my first spec section, if I look at view details, you can see that Aspen really has a lot of details in terms of designing your distillation column, right? You can see here that so this is a sieve tray, you can specify the hole diameter, you can specify a lot of, like, you know, the wear means the distance between the holes, you can specify the wear height, you can really specify a lot of details when it comes to your packing. So if you have a packing which is unique, you can always specify them your way. And then you can also change the type of correlation used to calculate your weep, your jet flood, and your maximum downcomer loading. I'm not sure if you covered these in mass transfer, but there are very detailed correlations out there. Fair correlation is very common. It's a very nice correlation. I actually like it a lot. Let's put fair here. This guy Fair, he's from UT Austin, I think, and he spent his life studying these, you know, packed columns, and he has very accurate and very, you know, comprehensive correlations for these types of phenomena. Anyways, but the idea is you can change a lot of these parameters. You know, if you become a distillation technologist, all of these will be relevant and actually important to what you do. But what I want to do is I want to go back to specifying my internals here. And this is what we have. And let's run the simulation with the new number of stages. So what we did, because we have flooding, first thing we did is reduce the reflux ratio. It didn't work out. So now I'm keeping the reflux ratio low, but I'm increasing my number of stages. And practically, you know, in practical operation, if you reduce your reflux ratio, you should always increase your number of stages, okay? Because you're reducing the flow rate going back in the column, so you need to give it more time to, you know, to separate. Okay, so I increased my number of stages. Let's run it. So everything ran fine. Let's have a look at the hydraulic plots and see if this resolved this flooding issue. Okay, it didn't really do anything for my flooding issue. So let's try a third improvement. Let's go back to my Radfrac column here, and let me push down my feed stage down a bit. So I increase my number of stages, however, the number of stages below the feed is the same. So let me push down my feed stage from 6 to, let's say, 9. Okay. Let's see if this makes any difference. Now let's run it and have a look. And now you can see like this approach or this iterative nature, now you're closing in on your exact design parameters for your distillation column. You're really understanding what stages are problematic, what stages where you're going to have the biggest difficulties when dealing with your column. Okay, let me close out of these guys and let's open the hydraulic results by themselves. Okay. Hydraulic plots, let's have a look. Oh, now it's getting worse, right? Now I'm having more stages with flooding. Okay, so how do we deal with this issue? Let's try to reduce our reflux ratio even more, or maybe we could yeah, let's reduce our reflux ratio more. I mean, there are ways to play around this, or actually, let's not play with reflux ratio. Let's look at our internals. Let's have a look at our internals here, and let's increase our tray spacing. Okay, so I'm gonna make every tray bigger just to give the fluid more time to eat up some of this hydraulic energy. So instead of 0.6, let's multiply this by 2. What's 0.6096 multiplied by 2? So it's 1 point, make it 1.22. Let's see if this makes any difference. Oh, and then, okay, let me change my stages to 9, and this guy will be 10. Okay, let's run this column and see if we get any different. Give it some time. It's running, calculating. Results, let's have a look at the hydraulic plots now and see if this changes anything. Okay, did it change anything actually? I don't think it did. So we're still getting a lot of flooding above the column. Okay, how do we fix this? Let's have a look at this number. It's 1.2 times 10 to the 5. Let me go back to my column. And let's see if I make this a bubble cap tray. It's gonna change anything. And again, I'm sort of going by trial and error, but you can always open your mass transfer book and try to do this logically, right? What I'm doing is not a very logical approach. But the idea is that showing you the utility of the Radfrac and how to use it in accordance with, or how to use it complementarily with your other tool. And as you can see, I mean, Radfrac, it's not giving you an error, it's running fine. If the flooding was severe, you have to understand that it will give you a warning or an error. As long as flooding is not severe, you should be generally fine to design this column this way. However, if you're really getting into the details, you want to have very minimal flooding, okay, in any of the stages. So having flooding in some of the stages, it's not gonna flag, it's not a red flag for Aspen, but it should be a red flag for you as an engineer when designing this column. Okay, Let me go back to the setup. Let's have a look here. How do we resolve this? Maybe I'm going to reduce my reflux ratio to 0.4 and like severely reduce the reflux ratio. And let's see if this makes any change. Okay, now I'm getting issues. Aspen is not happy. Give me an error. Let's have a look at the error. Following stages dried up, right? So when I reduce the reflux ratio a lot, I'll have some stages with no flow at all. And I think this is because we went below the minimum reflux ratio. So let's look at our shortcut methods, shortcut results here. Minimum reflux ratio is 0.76. So if I have a reflux ratio below this stage, I'm gonna have a reflux ratio below this value. I'm gonna have stages which actually dry up, and drying up means, you're sending back liquid, but it's not enough liquid to, to fill all these stages. Some stages will have no flow in them. And this is hydraulically not good. Okay, so let's increase my reflux ratio to 0.8, which is above the minimum reflux ratio suggested by the shortcut method. Okay, let's run this and let's see if this makes any effect on my hydraulic plots. Results available. Let's have a look at the hydraulic plots in this case. Okay, so in doing this, again, it has no effect on your on our flooding for this case. And there are many different ways you can do it. I'm gonna stop here. What I want you guys to do for this week is just play around with this combination of Radfrac and the shortcut method. See if you can find a way to avoid having flooding above the feed stage. Maybe Google it. I'm sure there's a lot of answers on Google and all these forums on how to do it. And if you're able to do it, submit your tutorial. Again, you can always submit this tutorial for points. And yeah, just practice around, play around on this combination of using the shortcut method and the Radfrac method to really get insight into the detailed design of the column, as well as the hydraulic details within every stages. Now you can use it to test whether you can use sieve trays or bubble cap trays, etc. to design your column. Okay, I'm gonna stop here. Thank you guys very much. If you have any questions, please come to office hours, and let's work through Aspen together, or the homework together, etc. You have until November 27 to submit everything. Thank you very much.